Hello, my dear students, and welcome to our lab discussion and debriefing of our results from the More Properties of Water lab. I'm going to go to our classroom here and show you what I'm talking about. So if I go to our classes and open up one of them and then go to classwork, you'll see a Properties of Water lab there at the top. That discussion and the examples of answers to the questions have already been posted, along with this lab, More Properties of Water lab, where we examined some more properties of water uh, or some variations on them. The first lab, we looked, for example, at cohesion, and this time we'll look at cohesion and adhesion in the concept of a phenomenon known as transpiration. So let's open up our More Properties of Water lab. Again, I'm working on an iPad right now, and I am working from a instructor's view, and we're going to look at some properties of water, high heat of vaporization. We'll look at high heat capacity as well, adhesion and cohesion as relates to the process of transpiration in plants. We're going to look at electrolysis of water, and instead of breaking hydrogen bonds, breaking the covalent bonds in the molecule. And we'll look at the solvent properties of water and what type of chemical compounds it dissolves. So let me open this up. You know that you can go up here to the top and you can open it, and then once you open it, you can save it or send a copy or share it if you wish as well, or copy it or open in a different program. You'll see all those options there. What I've done is sent a copy to myself into my files, in my files right here on my iPad at the bottom. And now I'm going to open it up in a PDF viewer, and that allows me to take advantage of and write and type in the fields. I do have my, whatever you call it, Apple Pencil to annotate with, but it, doesn't always work in every platform. So let me go through our experiment and discuss some of the results. We can go a little more quickly this time because I've already taken the liberty of filling this out and typing it so it's a little neater. So which substance had the higher heat of vaporization? Well, nothing has a higher heat of vaporization that I know of than water. Water has the highest heat of evaporation. And, in what order did the different liquids evaporate? So methanol evaporated first, followed by ethanol, then propanol, and finally water. So our next question says, why is water a much more effective coolant than alcohol for your body? And it's because those hydrogen bonds are very strong, and it takes energy to break them. You know that when you dry your hair and you use a hair dryer to dry the water, or you know that water dries more quickly on a hot sidewalk than a cold sidewalk because you're putting energy into that system. But that energy in the hydrogen bonds gets transferred to the water molecule that evaporates, so it has enough energy to break those bonds, and it carries that energy away. And I phrased it this way, as you can see on the screen. Water is an effective coolant because it takes a lot of energy to break the hydrogen bonds of the water molecules. When they are released into water vapor, they carry more thermal energy away. Because they took more energy to break those hydrogen bonds, they can carry more thermal energy away, but in this case, it's heat energy or thermal energy. And then I have this question from that I've used before in lab reports, and I've been corrected on it, but it says if the assumption question 2 is correct, Why do hospitals and medical professionals use alcohol to rapidly cool down a feverish patient? Here's my disclaimer. Hospitals don't do that anymore. They haven't done it since I was a little kid, and I guess I'm living in the past. A friend of mine who is a physician told me that you cannot do that because the children will sometimes inhale the alcohol and either become intoxicated, and I don't mean drunk. I mean they usually use isopropyl alcohol, so badly intoxicated, causing lung damage or other effects and symptoms. And the rapid cooling really only cools down the skin and doesn't do an effective job of cooling people down. If they have a fever, they put them into cool, not cold water, and cool them down that way now in a hospital environment. But alcohol is great for cooling things down due to evaporation. Even though water carries away more energy for each water molecule, what I wrote, and your answer should say something like this, or say this if you wish. You may put in your own words as well. Alcohol evaporates much more quickly, and though each molecule carries less energy, the rapid rate of evaporation gives greater, faster cooling overall. So each molecule is carrying less energy, but there's so many of them, you can carry away a lot of heat. You know that from putting alcohol on your skin and blowing on it. You can get a quite chilling effect. Why did the longer chain alcohol take longer to evaporate than the shorter chain alcohols? Well, I've already said this. Methanol has 1, ethanol has 2, and propanol has 3 carbons. It's 3 carbons long. And we learned about dispersion forces, and we said the thing that affects them, that determines how strong they are, is the number of electrons that are there interacting. Well, the more atoms you have, the more electrons, the more outer shell electrons you have to produce these dispersion forces. And therefore, as I wrote here, the longer chain alcohols have more atoms and therefore more electrons. So the dispersion forces, it's one of the 2 types of van der Waals forces. So the dispersion forces holding them together are greater. And why did water take longer to evaporate than all of the alcohols? Well, you know that. Water is slower to evaporate because those hydrogen bonds individually are weak, but collectively are quite strong, and they're much stronger than dispersion forces. So water is slow to evaporate, but when it does, it is a wonderful cooling substance, but only if you don't have high humidity and evaporation can occur. Anyway, water is slower to evaporate because those hydrogen bonds are holding it together. Those hydrogen bonds are stronger than the dispersion forces. The question was, why did it take longer to evaporate than the alcohols? It has stronger bonds holding it together. So we looked at some celery and some flowers that I put into water with food coloring, and we saw that they took up the food coloring all the way up to the top of the flower petal. And describe what happens when you place the celery into the water with the dye added. The dye rose all the way to the top. This was not capillary action like in the little capillary, where it only jumped up so far until the weight of the water column, which weight is a force, equaled the forces of the bonds, the hydrogen bonds adhering to the glass and to each other. So in this case, somehow the dye rose all the way to the top. And it's because there's water evaporating out the top. And as it evaporates, the next molecule, water molecule, is pulled into place along there. And it says, find and give me a definition for transpiration. And what are some similar words? Well, transpiration is the transport of water from the roots to all the tissues of the plant. And some similar words might be transportation, or we'll just do transport. I can do transportation. How about evaporation? Sounds familiar, huh? Maybe a little, the Asian part. Perspiration. Perspiration. I'm not sure how you spell it. There we go. perspiration. And that's exactly what you have is molecules evaporating at the stems and the leaves and the petals. And as they enter the vapor phase, the next molecule moves into place and pulls it up all the way down to the roots. And what types of organisms depend on this property of water? Plants, of course. They don't have a heart to pump fluids throughout the organism, but they do have a vascular system, xylem and phloem, as you'll learn in biology. And these xylem transport water from the roots up to the highest part of the plant and to all the parts of the plant. Because there's no water up there in the air, they have to use this process of transpiration because the only place water enters the plant is in the roots in the ground. Most plants. Okay, now in this next property of water, we looked at what components water is made of, and we hooked up a battery to 2 electrodes. We used the pencil leads of pencils for electrodes, and we saw bubbles being produced, hydrogen and oxygen gas being produced as we passed a current through the water, which had in it an electrolyte. I just used baking soda or sodium hydrogen carbonate. So does one pencil produce or collect more bubbles than the other? Which one? Yes, and it's the negative electrode, which, by the way, is also known as the cathode, or the place where the reduction takes place. But the negative electrode produces twice as many bubbles as the positive electrode, or the one connected to the positive pole. And why do you think this is? Well, there are twice as many hydrogen atoms as there are oxygen atoms in the water molecule. And it says what gas is being produced at each electrode. Hydrogen is produced at the negative pole, and that is the cathode, but we don't need to worry about cathode and anode. And oxygen was produced at the positive pole. And it said, what use would these gases be if you could collect them? Well, hydrogen is a wonderful clean burning fuel because when you burn it and combine it with oxygen, the only thing you make is water. It's non-polluting, and it's, I won't say practically free because electricity costs money, but the hydrogen, there's plenty of water in the world, so there's plenty of hydrogen. And at the same time, we produce oxygen, which can act as an oxidizing agent. For example, in many rockets, you have tanks of hydrogen and tanks of oxygen. And when you burn that hydrogen in the presence of pure oxygen, it burns very violently and very explosively. It tends to do that anyway, even in our atmosphere at 20% oxygen. So it's not a perfect fuel because it has what? The hydrogen requires high pressure. It is a gas, so you either need to liquefy it and use extreme cold temperatures, or you need to use high pressure tanks and lines and things. So there is some expense, but it's very simple, clean burning fuel. Of course, oxygen is used in hospitals, especially these days during this COVID crisis. Many people are on oxygen. The next question you don't need to answer because we couldn't do it. I found 4 solar cells in the lab, but I didn't have a sunny day to go outside and do the experiment. But just think, if you're not paying for the electricity, if you're not using batteries that cost $1.50 like we were using in the lab, if you're not paying for the electric from your electricity provider, but you're using solar cells, to power the splitting of water to collect hydrogen, it really is free fuel. And I look up there at that sun and see how bright it is, and it's basically a big fusion reactor. And I think our society is being very foolish when there's free energy, but there's no way for people to make much money off of it. So I suspect that's why we don't have it. It says, what are the roots and origins of the word electrolysis? Well, it's 2 roots. Electro, which refers to electricity, which actually comes from the Latin word for amber, the yellow it's almost like a mineral in that it's used in jewelry and rings, and like a semi-precious stone because it's hard and it can be polished, but it's actually dried pine sap. But the thing about amber is if you rub it with a cloth, it's a great source of static electricity. And in the beginning, when people were studying electricity, amber was their source for electricity. It was always, of course, DC static electricity, but amber relates to electricity, at least in the old days. And lysis, of course, comes from the Latin and Greek. It comes from the Latin, but the Latin got it from the Greek. Words for loosening, and in modern usage, lysis usually means a splitting. So, like a lysosome in the cell is where you split up your food molecules. So, electrolysis does not refer to killing of hair. There's a process where electric current is passed through hair and kills the root, and is a good way to depilate or remove hair permanently. But in the chemistry lab, it refers to the splitting of water using electricity. And finally, we explored the solvent properties of water, and we tested 4 substances: table salt or sodium chloride, an ionic substance; table sugar, which is a very polar substance, but is not charged. It's just polar, so it has unequal charge distribution in its bonds. We used a very nonpolar substance called mineral oil, and we also used an ionic salt, calcium carbonate. And calcium carbonate is ionic, but it says which substances did not dissolve and why. Calcium carbonate mineral oil did not dissolve because calcium carbonate forms an insoluble salt. Even though it is truly an ionic compound and when molten will conduct a current, it does not dissolve well in water. It will dissolve in acid, but not in water. Mineral oil is a non-polar liquid. You might as well be adding vegetable oil or motor oil or gasoline. It floated on top and it did not dissolve because it's non-polar. You need a non-polar solvent to dissolve it. It says compare and contrast the terms polar and non-polar. And polar substances have poles. That's their inherent in their definition, that have opposite charges. Non-polar substances do not have polar bonds and have a uniform charge distribution. Electrons are shared uniformly and equally in a non-polar covalent bond, and the electrons are shared unequally, creating a unequal charge distribution in a polar bond. And here, why didn't the ionic substance calcium carbonate dissolve, and where can it be found in nature? Well, calcium carbonate is soluble in acid, but it's just insoluble in water. Most carbonates are insoluble. The common one that I can think of, sodium carbonate and sodium hydrogen carbonate or sodium bicarbonate or baking soda, does dissolve, but very few other metal salts of carbonates do dissolve. And calcium carbonate is a great sink for CO2. From our atmosphere, from our water, and everywhere else, but it can be found in the shells of mollusks. This is clams and oysters, seashells and snails, and a group of small organisms, the foraminifera, which have shells of, they're microscopic, but they have shells of calcium carbonate. They're a class of algae or protozoa at least, and they all fall to the bottom of the sea, and if that mineral deposit gets lifted up, it's chalk, and if it sits under great pressure for a while, it becomes limestone, and if it sits under great pressure and heat for a while, it becomes marble. And those are all simply calcium carbonate. So that concludes our discussion of our more water water properties of water lab, the more water assignment, or the more properties of water lab, this one right here. And again, I'll remind you that these count as a test grade. So you want to complete this and hand it in because, frankly, it's an easy A. So my gift to you, I'm sorry this took me a while to record and get done. I've recorded it several times. I've had sound problems with my computer and recording problems and recording errors and uploading errors. So we will see if this one gets to you. And I will make it due a week from now. So don't worry about your time frame. And we will see you in the next discussion we post. And until then, stay safe and stay warm. And I